This is the CYK algorithm by Adam Glodin and Derek Pearson. Some background: the CYK algorithm was originally developed by J. Cocke, D.H. Younger, and T. Kasami to determine if a string can be created by a given grammar. To use the CYK, the grammar must be in Chomsky normal form. Our CYK algorithm is based on an alternative formulation of Cocke-Younger-Kasami's algorithm by Peter R.J. Osvald. So this is the algorithm. First we assume n is the size of the string and t is a matrix size n by n plus 1 to store our computations. So we loop from 0 to n minus 1, and this determines our first row of variables that produce our terminal symbols. Our second loop loops through our row and concatenates the two previous non-terminal variables and checks to see that if there is a variable that produces this variable pair. Then finally, at the end of the loop, the string a1, a2 to an is in our language G if and only if s, our starting symbol, is in T sub 0 n. Okay, so now we'll look at an example. We'll use the following CNF grammar and string to check our algorithm. On the first pass, we'll go through our first loop and we will find the non-terminal symbol that matches our terminal symbol. So we have big A that produces little a and big B produces little b. So we map these to the matrix as AA, B, B, B. Now the second part. We're determining the second row. So the first time through, we have D equals 2, I equals 0, J equals 2, and K equals 1. So we have B equals T01, which is A, and C equals T12, which is also A. And since nothing produces AA, the empty set is stored in Tij. Now for the next row, D equals 3, I equals 0, and J equals 3. So for K equals 1, we have Tik equals T01, which is A, and Tkj equals T13, which is S and B. BC equals AS or AB. So for K2 we have Tik equals T02, which is our empty set, Tkj equals T23, which is B, and BC equals T01, which is the empty set B, which is the same thing as B. So BC equals AS or AB or B. And since S and B produce AB, Tij is set to S and B. Nothing produces AS or B, so they are ignored. Matrix T is then finished similarly as shown before, and if our starting symbol S is in the last filled box, then the grammar produces this string. In our example, since S is in T05, AA, B, B, B will be produced by the grammar.
We will now get into our code implementation, which is written in C# in a console application. So in the main function, first thing we do in this, we will get our grammar from the user, which just reads in a text file. They enter a name. In this case, it's grammar. It has this Chomsky normal form grammar. And then we will find a value to find in the grammar to see if it is in there or not. And then we will initialize the matrix using that value's length. And then we pass our value into our CYK algorithm. And as before, in the first pass, we get each character in the string, and if our grammar contains a production that produces that character, we'll add the variable that produces it into our matrix in that location. And then the pass 2, we will go through everything else in the matrix, and for the D, I, J, and we'll go through each K between I and J and find variable that will produce it. So we pass in the TIK, TKJ that we had before, and we'll concatenate them together. And if our productions in that grammar produce the concatenation of the two, we'll add it to our TIJ. And after the algorithm, we will print the matrix out to the user, and then we will print whether or not we found the value in the grammar, if the grammar can produce the value. So we'll run it. Our name of our file is grammar, and we'll find AA, BBB, as in our example before. And here it's printed out a little nicer to read, and you can see that S is in the top one, so the value can be created by the language.